Nice to meet you all. I'm very happy to be here. That's my first SciPy ever. And I'm really excited to talk about what I did with my colleagues here at our physics experiment at LHCb. So let's get started. Let's put in some context. We work with CERN. CERN is, for those of you who don't know, the European Organization for Nuclear Research. It is located right here at the border of Switzerland and France. Here you can see Geneva in the background and a little bit of the Mont Blanc and the La Clément here. And this CERN facility hosts the biggest ever built machine, the LHC, which is outlined here in yellow. It is a particle collider. It collides protons. It is super big, 27 kilometers circumference, to be able to get the protons to super high energies. And it collides them in two contra-rotating beams. So here you see my cursor, right? You see the blue bunches and the red bunches. They go left and right. And they collide at four very specific points here. And every point, when they collide, there's a detector around that. And those detectors try to record everything that happens during the collision, which is a lot. These detectors you can simply think of as super high resolution cameras that can do things every 25 nanoseconds. Okay. For an idea of scale, this is a very small part of the collaboration that we work in at LHCb. Here in the back, you can see a little part of the detector. These are tracking stations. So these are used, for instance, to, when a particle traverses through, you will see light to be emitted at the point where it traversed through, and then you can reconstruct where the particles went through in the detector. Here's a cool picture. This is our magnet, our dipole magnet, used to bend the particles such that we can have an idea about what momentum they had. So this is as big as one of the smaller conference rooms here. Okay, so this is how this looks then when we see collisions. So the protons come from this side, and they collide in this little detector here called the vertex locator, the velo. And then all these tracks, all these particle trajectories that we will in the end reconstruct, go through this detector. They bend here through the magnet. They will be recorded in tracking stations, so the ones that give us the position. And then you'll also have information from other subdetectors, so it's a bunch of them, that will give us information about the type of the particle, so whether it's a proton, an electron, a muon, or whatever. And this happens every 25 nanoseconds, and a lot of stuff happens every time, so we have an insane data rate. In 1 year, we produce about 15,000 petabytes of raw data. That corresponds to a nominal data rate of 5 terabytes per second, which is roughly 5% of the global internet traffic. So quite a lot to be processed. But of course, we can store all of this. We only have this little blob of storage here, 30 petabytes per year. So our task, in a nutshell, is get this big blob to be the small blob in real time. So we have a trigger system that tries to select in real time. It's a big classification task. And ideally, of course, as in every classification task, we want to keep the things that are interesting and discard all the rest. So the little data nuggets in this big blob, we want to make sure we get those. Okay. So when I talk about selecting interesting data, what does that even mean? Unfortunately, we don't yet have any big classifier to tell us that yet. And it will be complicated to make one of those, because different things mean different people have different definitions of interesting. So we have about 1,000 different people. They all care about different parts of the physics that happen during a collision. And we want to try to accommodate all of them. So to each their own. Our definition of interesting is a union over 1,000 different and constantly changing opinions. So what we want people to be able to do is design their own heuristic. They design what is interesting. They design this part of the code. So what people, for instance, look at are decays of longer-lived particles, like this B meson here. It is created in one of those proton collisions, outlined in this little explosion here. It flies a little bit and then decays into something. Some things, only a few of which can actually be seen in the detector, only if they're charged. And then another one of these decay particles might again decay into something else, and then we have this kind of signature. So people want to select for something like that, or 1,000 other different things. Okay, so the gist so far, we have a bunch of data, we have very tight time constraints, we have many people that design small parts of the system, so we need something that runs fast and is easy to extend. I think that's every software developer's dream. Okay, so what do? We've played this game for almost 20 years now, I'd say. We started off with our low-level language of choice, C++. We need to be so bare metal to be able to get our performance up to speed. But the people nowadays mostly know Python. The people who work in a physics experiment do a lot of data analysis, and as we all know, Python is one of the best choices for that. But we cannot just write in Python, that's too slow. Even if we do things like call C subprograms like NumPy does, for instance. That just doesn't work. So we want the best of both worlds. We define a small number of algorithms that are very high performance in C++. We make them somewhat configurable such that they can be used for in different scenarios, depending on what people want to actually select for. And then we want to configure the whole application in Python, but not lose any performance. Okay, so this is how it goes. We define C++ algorithms in our code base. They show you an I/O signature, so what comes in, what goes out, and a couple of configurable properties, so that they're versatile. During the build step, we then generate algorithm representations, so simply Python classes that mimics the input and output behavior, and it carries the properties. We can then use these classes, instantiate them, give inputs to outputs, and so on and so forth, and build a dataflow graph with that. And then we can configure these representations. And all of this information will then be given back to C++, and then we have a fully specified C++ application that can run at 0 overhead. Okay, and we want to be focusing on this part today. Okay, so let's build a mock dataflow graph, something fairly easy. We try to build a tracking flow now. So tracking means look at the detectors that find you hits, so where the particles went through, and from those reconstruct the lines of where the particle went through, particle trajectories or tracks. So in this example here, we have the velo detector, that is one of the tracking stations. We have the magnet which bends the particles, and then another tracking detector back here. We start our dataflow graph always from a single source, which is the input reader. It reads from memory or from file or whatever. And this is the first algorithm representation that will be instantiated here. As soon as it's instantiated, it is immutable, so you can put a breakpoint here and then reason about the configuration of any representation at this point. It exports an output here, for instance, the raw data, that we can then give to an input of the first decoding algorithm. So this takes the raw data that is packed, unpacks it, and tells us where the hits are in the detector. So now we have little dots in the velo and all these layers that tell us, okay, a particle went through here. Then we can take the outputs of this velo decoding, the detector hits, and give those to the input of the velo tracking. So we can build the first straight lines here by fitting points to other points and see if we can see a straight line. And we see a couple of them, and from this we can continue. Now we do the same deal in this other detector. We take the raw data and decode that. Now we have hits here, and then we use these tracks and the hits here to try to find the whole trajectory. So from the beginning of the velo to the end of the SciPy, basically. And now we have full tracks. This SciPy tracking algorithm, also one that was generated, right, exports these tracks as output, and we can ask for every output we can ask how it was produced, and it will give us the data flow back, basically, as a nice visual graph. This is a simplification of how it looks, but as you can see, okay, we take the input reader, it exports raw data to here and here. These build us detector hits, and velo tracking gives us a track, and then with the SciPy tracking we will get our tracks. Okay, this is how it actually looks. So in a non-simplified version for a very small data flow. can see here the outputs in red and the inputs in blue. And then here are a couple of configurable properties. Okay. One thing that I want to talk about if we do things like that, our data flow is generated within a pretty deep call stack. So if you ask for kaons, then the kaon function will ask for particle trajectories, and then the particle trajectories function will ask for decoding and for tracking and all these things. So by the time we have kaons, we're already in a, like, I don't know, 10, 12, 15 layer call stack. Now our software is deployed to a read-only software distribution service. For those who know CVMFS. So we have built a default data flow that people should use, but not necessarily have to, such that they don't have to write the entire thing by themselves. And we release that regularly, but people still want to be able to tweak everything. They want to, deep within the call stack, look at, now instead of doing this, I want to change this little thing. There's an example, a somewhat good example of that. So imagine the people call use tracks. And use tracks is a function that gets us tracks with a high momentum and does anything with them. And the high P tracks maker, so this function here, builds us tracks and filters them by a minimum momentum requirement. But now what if I want to change this to 2 GeV? So I want even higher momentum tracks only. As you see here, if we call use tracks, there's no argument here. We don't have any way to access the default argument of that and change that. So what we can do, of course, what is like the first solution that one would come up with is to just pass this through. So give the use tracks a min p argument, send this through to the high p tracks, and then change the argument as such. But now if you think how that scales, for everything we want to tweak now, we have to pass the arguments through the entire call stack. And it is a lot of things that we want to tweak. So now every function signature would basically be infinitely large. And we really don't want to do it like that. Also, another drawback is that if we pass it through, this default will become meaningless because it's never, we always give an argument, so this default will never actually be used. So what we do is we take a little bit out of the book of Google Gin config. Maybe people know that. We define a little configurable wrapper that lets us tweak default arguments of anything. So as soon as you have access to this function from wherever you run your top-level code in, you can make a new context and bind a new argument, a new default argument to this function. And then if you use this function somewhere in your call stack within this context, make high P tracks will now run with a default of 2 GeV instead of 1 GeV. Okay. Now the last part that I want to go to is selecting relevant physics. A large part of the configuration is observable-based selection. So examples of that would be people only care about tracks that have more than 5 hits in the detector, or reject particles that have less than 2 GeV momentum, or accept vertices that can be reconstructed in a fit that then has a fit chi-square of less than 3. There are a gazillion of those. And as we don't want to implement a gazillion things, we want to be able to compose and combine them. People care about all the different combinations of those things. So as soon as you hear compose combine, you think about basic building blocks, and we have these things. We call them functors in the C++ sense, so callable function objects, and they define a minimal DSL. We allow logical operations on them and functional composition. So how this would look is somewhat resembles the Haskell point-free syntax, but not quite. So if one wants to select high momentum kaons, and the input is all the particles, then we can define a selection as such. The particle ID, PID, that's an operator that takes a particle, a functor that takes a particle, gives us the type of that, should be equal to kaon. So now this, from something that has signature particle to PID, give me a particle to bool, if it's equal to kaon. And we combine that with a momentum requirement. So the momentum of the particle should be bigger than 2 GeV. Momentum operator, take a particle, get float, combine it in this logical manner here. This will now be an operator that takes particle, gives me bool. And then we send this selection into a filter algorithm, and then we can use that in our data flow. And this will be compiled into something that has 0 overhead in C++. So how does this look in Python? We have the Functor object. It has a name. It has a corresponding C++ implementation. So this is the namespace in the struct. And then a docstring. And the momentum functor is already a composed functor. So we have these building blocks here, magnitude and 3 momentum. 3 momentum takes a particle, gets me the 3 momentum vector, and the magnitude gives me the length of that. And then if we combine them in the functional composition way, now we have something that gives us the magnitude of the momentum. Okay. This is how it looks in C++. This is the very easiest it can look. Here, so this is the corresponding C++ implementation here. It is a struct that has an operator, a parenthesis operator, such that it's callable. It is always templated, such that we can dispatch to different types of particles. And then it simply returns the PID here. In this operator, you can do whatever you want, but this is an easy way. Okay. So then a little bit more real-lifey. How do we use these compositions to do reasonable things? One thing we care about is minimum distance to. That is a functor that takes a particle and tells us how far are you away from a list of primary interaction points or vertices. So why do we care about that? I outlined at the beginning that we care about long-lived particles like the B meson. And if it comes out of these primary interaction points, imagine multiple in there, then it flies for a while, and then it decays into something. And if things, like the muon here, come from a displaced vertex, so one that is far away from the primary interaction points, then it will, when extrapolated, not point back to them. There will be a non-negligible difference here between these interaction points and the extrapolated track. And we want to know how big this little line here is. So what we do, we take a couple of building blocks. The distance functor, very easy, takes as input 2 things and gives me a distance, a float. Now we lift this operation. This is like a Python map, but point-free. This makes this function have a different signature, namely a collection of x's and a y, and a collection of distances. Now, what we want to give to the filter algorithm is something that only takes in a particle and not the vertices. So we do something like functools.partial or bind front in C++, which binds the vertices to the first argument of this. And now the new signature is 1 particle to a collection of distances. But because we want the minimum, we do one more functional composition, and then we end up with a function that takes 1 particle and gives me the minimum distance to all the vertices. Okay. Now, these Python compositions will generate a C++ code where you can choose your backend. So, as you have seen, they are all templated. So, if you want, you can run them in a vectorized mode. We always map these selections over a collection of particles, right, to select them. So, anything you can do at the same time over 8 particles at once, for instance, and then use an AVX instruction to speed up your thing. And everything that people build anew, that people change in the default code base, will be just in time compiled, on demand during the initialization of our program. All right, so let me conclude. We have lots of data, we have little time. We need to be very fast. So the best guess is a low-level language like C++ and very high-performance code. Now we could stop here basically and just let all the people write C++ code. We have tried that in the first 10 years. It was a big mess. So what we rather want to do is to have them write things in their language of choice, which is Python. So we generate our data flow, we build our data flow, and the selections that I've shown you in Python. We have guarantees about consistency. Things are immutable as soon as they're instantiated. The data that we send back and forth is type checked. And we have good methods of inspection, like plotting the data flow and putting breakpoints anywhere, which is, if you've ever dealt with a big C++ code base, GDB is fairly hard sometimes to get to work. But in Python, just set a breakpoint and it's all great. Okay, and then we take all this information that we've built in Python, we translate it into a humongous dictionary, basically, and we code generate the selections. We give all of this to C++, and then we have a pure C++ application that we can run 0 overhead. Thank you for your attention.
Okay, thanks for that very nice talk. We actually have plenty of time for questions. So I think I know that there's some in the chat, so I'm going to read those out loud and you can have some time to respond. Sorry, let me pull these up. Okay, so in full disclosure, I asked this first question, and I'm also on an LHC experiment. Okay, so while PyConf is built to be specific to LHCb's geometry and physics needs, are there other experiments in the broader particle physics world here that use a similar approach? Is LHCb unique here? And are there underlying representations of PyConf that you think would be general enough that could be useful to other particle physics experiments or even more broadly other communities?
Okay, so this thing is fairly deeply integrated in LHCb. Other particle experiments also use Python for configuration, depending on where you work, maybe Atlas?
Yeah.
Okay, so Atlas also uses the underlying thing, which is called Gaudi, and they also, they do the Python translation part. I actually wanted to give this talk because I would want to see if other people are interested in using that. So if there's interest, then I would make it more standalone, which is probably not too hard to do. What's the last question again?
You kind of answered it, but it was, are there is it something that you think there's underlying representations and the hooks to Gaudi to make it useful to other experiments or other communities?
Yeah, for sure. Yeah, I think so. Yeah.
Okay. And then we have another question from Benjamin Glass. Is the source code for PyConf available publicly online?
Yes, it is.
Okay.
I think that should be in the abstract of the talk, but if not, then can I edit this later?
Sure.
Yeah. I will put it somewhere so that people can see that.
Okay. And then we have one more question. So it looks like the min distance 2 example is using Python typehints. Is all of PyConf using typehints? And if so, can you comment on the development experience of using typehints for a large database or a large code base like this?
Sorry, can you define typehints? What is that?
Oh, just what's being done here.
Right. Okay. We use that as consistently as we can.
Okay.
Given that a lot of people write, not necessarily this type of code, but the things on top of there, we don't get. Is there a way to enforce this everywhere? Maybe.
Okay, but you don't use like MyPy or something.
No, we don't do that.
Okay.
When I talked about data type matching, that is done behind the scenes with Gaudi, actually.
Cool. Okay. So let's thank our speaker once again, and we'll go on to the next talk.